Hello everyone, welcome to my video on the U substitution for definite integrals. So in the previous video we saw the U substitution for indefinite integrals where I provided you with a strategy to solve. The same strategy applies for definite integral. The only major difference is the fact that indefinite integrals gives us a class of functions or a family of functions, whereas now for a definite integral we're going to apply U substitution. There's one slight little detail that changes, but in essence we're getting an actual value which represents the area under the curve. So let's go ahead and look at the theorem. So it states if g prime of x is continuous on the closed interval ab and f is continuous on the range of u, which is equal to g of x, then the integral of a to b of f composed of g of x times g prime of x dx. We've seen this before. Essentially, again, the U substitution is essentially chain rule for calculus 2 for integration. So we have this composition of functions and we're multiplying by the derivative of what's inside the function f. So you're taking g of x, you're multiplying by its derivative. Everything here is in terms of x, and that's equal to the integral of g of a to g of b of f of u du. So the left hand side of the equation is expressed solely in terms of x, whereas the right hand side of the equation is expressed solely in terms of u, just like before. Nothing's changed except for the fact that now the bounds of integration are given. Here we have a to b, and what's really important here, and what you cannot forget, is when you have a definite integral for U substitution, you have to change your bounds. You have to change them in terms of u. Notice here it's a to b. Here it doesn't go from a to b. It goes from g of a to g of b. So you have to change the bounds of integration. Okay. There's a way of doing this where you could essentially leave the bounds empty until you come back at the end, and then when you bring the whole function back in terms of x, you bring back these bounds of integrations. But in general, I think it's better to actually just switch the bounds and integrate it in that fashion. I think that's the most efficient way, and that's the way I'm going to show it to you in this video. So let's go ahead. I'm going to skip the strategy. If you want to look at the strategy, go and look at my previous video. Let's go ahead and look at a couple of examples. So in our first example over here, we have to evaluate the integral from 0 to 1, the definite integral from 0 to 1 of x times x squared plus 1 to the exponent 4 dx. So go ahead, pause the video, give this a shot, see if you're able to solve the problem. So what did you call your u? This is the question. My thought process is the fact that we have a bracket. What's inside the bracket is x squared plus 1. If we think of its derivative, the derivative of x squared is 2x. And we have an x sitting on the outside, so that to me looks good. If you're thinking of expanding this 4 times, you will get the same answer, but you don't want to expand it 4 times, especially if this was like 40 or something. You don't want to expand it 40 times. So this is why U substitution is the more efficient way of doing things. Okay, so if we let u equal x squared plus 1, its derivative is sitting on the outside, so the derivative du is equal to 2x. And we're deriving with respect to x. Isolating for dx by cross multiplying, we get du divided by 2x is equal to dx. Okay, so this is equal to, from 0 to 1, right? Wrong. Not 0 to 1. We're integrating from 0 to 1. This is the integral with respect to x. Now that we're making the substitution, we're switching this in terms of u. You have to change the bounds also in terms of u. How do we do that? Well, you don't have to write this out. I'll do it for the first time, but focus on the upper bound. So if we look at the upper bound, in this case in terms of x, it's 1. So the upper bound is x equals 1. We want to express the upper bound in terms of u. So we know that u is equal to x squared plus 1. So what you're essentially doing for the upper bound is substituting the x with 1. So u equals 1 squared plus 1. 1 squared is 1, 1 plus 1 is 2. So the upper bound here is now 1. Now that we're applying this u substitution, we have to switch it and write 2. Okay, let's do the same thing with the lower bound. So for the lower bound, the lower bound is x equals 0. Using the substitution not u squared, just u equals x squared plus 1. X is being replaced with 0, so 0 squared plus 1 gives us 1. So the bottom here is going to be a 1. Okay, so we have to switch the bounds of integration. Now that we switched, let's replace everything that we know. We have our x that has to stay. We can't do anything about that. Inside the bracket, x squared plus 1, we're going to substitute it with u. So we have u exponent 4, and dx, we're going to substitute it with du over 2x. Okay, this is our job. This is where we have to go ahead and simplify. Thankfully, the x's cancel, leaving us with an integral written or expressed solely in terms of u, which is what we need. The 1/2, let's pull it out, and we're left with just 1/2 integral from 1 to 2 of u to the 4 du, which is easy to do. We use power rule, so we add 1 to the exponent and divide by that value, giving us a 1/2. And we get u to the 5 over 5. And we're applying FTC part 2, where we evaluated at the upper bound and the lower bound. Now, you do not have to go back in terms of x. Because it's defined from 1 to 2, we change the bounds. We could just substitute the upper bound 2 and the lower bound 1 and get our answer, and we're done. Had you not switched the bounds, you could have skipped this whole step, not skipped the bounds, and then at this stage here, instead of going from 1 to 2, you would substitute it back to x. So you would write this as x squared plus 1 to the 5 divided by 5, and the bounds of integration would stay as 0 and 1. So that's really up to you how you want to solve it. I think it's better to always change the boundaries, but that's my opinion. You can do it the way you want. So I'm going to keep it as 1 and 2, and I'm going to substitute my boundaries, which are expressed in terms of u, at this stage now. So the 1/2, maybe the 1/5, I could pull it out at the same time, giving me 1/10 on the outside. And we're going to apply FTC part 2, where we substitute 2 in the u, so 2 to the 5, minus the lower bound, 1 to the 5. This gives us 1 over 10. 2 to the 5 is 32. 1 to the 5 is 1 minus 1. This gives me 31 over 10. And that's the answer. We're talking about area, so it's units squared, and we are done. If you substituted back into x and substituted with 0 and 1, you would get the same result. So you should get 31 over 10. Okay, let's take a look at the next example. So in the next example, we have to evaluate the integral from 1 to 5 of dx over x minus 3, all that squared. The dx, you could kind of ignore it if you want. If this notation bothers you, you could put 1 over x minus 3 squared and the dx on the side. That's the same thing, but typically the dx is written on top. That's just the same integral, just with different notation. So let's go ahead and solve this. I urge you to pause the video, give this a shot, see if you're able to solve it. So if you went ahead and you let u equal x minus 3 and solved it, and you got 1 over u squared, you changed your bounds, this is wrong. Okay, this one over here is a definite integral. You have to recall, for definite integral, it only works if the function is continuous and defined on the closed interval from 1 to 5. Is this thing continuous? No, it's not, because if you substitute x with 3, you're going to get 3 minus 3, which is 0. 0 squared, you're dividing by 0. X cannot be equal to 3. And is 3 in the bounds of integration? Is 3 in between 1 and 5? Yes, it is. So this integral does not exist. You do not compute it. Don't compute things blindly. You really have to ensure that the function is continuous on the interval that we're dealing with, okay? In order to apply FTC part 2 and to take the definite integral. Okay, so be very careful. That's my warning to you. Look out for that. Always ensure that the bounds of integration are satisfied and there's no issues with the function, okay? Let's move on to the next one. So in the following example, we have to evaluate the integral from 0 to 4 of dx divided by 1 plus 2x, all that to the exponent 3/2. So pause the video, give this a try, see if you're able to solve the problem on your own. So the first thing you should have done is just ensure that there's no issues with the function. Don't fall for that trap. So is this function continuous? No, it's not. We could divide by 0. So 1 plus 2x equals 0. That's not good. 2x equals -1. X cannot be equal to -1/2. So if x is equal to -1/2, that would cause the whole bottom to be 0, right? -1/2 times 2 is -1. -1 plus 1 is 0. 0 to the exponent 3/2 is still 0. So you're dividing by 0. Is that an issue for us? The fact that it's not continuous at -1/2 is not an issue because we're dealing with the interval from 0 to 4. So it's not continuous at -1/2, but that does not fall in our interval, so we're good to go. Let's go ahead and apply our u substitution. So you have to keep this in mind. So what's the u substitution that we use in this case? Well, the u substitution is 1 plus 2x. Like u equal 1 plus 2x. If you take the derivative with respect to x, you get just 2. The derivative of 1 is 0. The derivative of 2x is just 2. Cross multiply for dx. Think of this as 2 over 1. We cross multiply, giving us du over 2 equals dx. So we solve for dx. Let's go ahead and substitute it into here. So the next thing we have to do is recall that this is a definite integral, so we have to switch our bounds of integration. We're applying a u substitution on a definite integral, change your bounds. So your upper bound, I'm not going to write this on the side. If you want, you can write it on the side, but we're just replacing the x with 4. So for the upper bound, we have 2 times 4, which is 8, plus 1, which is 9. So this is just 9. And the bottom is 0. If you substitute 0, 2 times 0 is 0, plus 1 is 1. So the lower bound becomes 1. What we're left with here is dx is rewritten as du over 2. So du, I'm going to take the 2 on the outside, or not the 2, the 1 over 2, and put it as a half on the outside of the integral. And the bottom we have over u to the 3 halves. Okay. So this integral is a lot easier to deal with. I'm going to remove the du on the side, just because this notation may seem confusing, but it shouldn't bother us all that much. We have the 1/2, the integral from 1 to 9, and the du is going to be sitting over here. Really, you should be thinking of this as 1 over u to the 3 halves, which can be rewritten as u to the negative 3 halves, right? It's downstairs, we're bringing it upstairs, we switch the sign of the exponent. Okay, so if you don't believe me, do it this way. Think of this as 1 over u to the 3 halves, and then du next to it. Okay, so this is equivalent to this, and now here we could just simply use power rule. Add 1 to the exponent and divide by that value. So we have the 1/2 in the front. Taking the integral, we have u to the negative 1/2, because negative 3 halves plus 1 is negative 1/2, divided by negative 1/2. And we're integrating from 9 to 1. Alright, this is a definite integral, so again, there's no plus c. You're using FTC part 2. You're evaluating it at the upper bound and the lower bound. And since it's a definite integral, we don't have to go back in terms of x in this case, because we're just going to substitute our boundaries. Okay. So let's simplify this. This is equal to 1/2 times negative 2u to the negative 1/2. And we're substituting 9 and 1. The negative 2 divided by 2 is negative 1. And the u to the negative 1/2, you can think of it as 1 over square root of u. Okay. And now we could evaluate the upper bound and then subtract it by the lower bound. So FTC part 2. So we have the negative 1 on the outside, and then we have 1 over square root of 9 minus 1 over square root of 1. Square root of 9 is 3, square root of 1 is 1. So we have a third minus 1. This is equal to negative 1, 1/3 minus 1. 1 is the same as 3 over 3. So we have minus 2 over 3. And because there's a minus in the front, this ends up being positive 2 over 3 units squared. And this is the final answer. Okay. So let's go ahead and keep practicing. So in the following example, we have to evaluate the integral from 0 to pi over 2 of cos of x times sine of x dx. So go ahead, pause the video, give this a try, see if you're able to solve it on your own. So the first thing I'm going to do is use a u substitution. Sine and cos are continuous functions, so we don't have to worry about that. And the composition of continuous functions is again continuous, so continuity is satisfied. And the substitution we're using here is sine of x. Okay, specifically this one here, the one that's inside the bracket. It's not a multiplication, it's sine of x. It's composed, two sine functions that are composed in one another. So the one inside is what I'm calling u, because I know the derivative of sine is cos, and the cos is sitting out here in front. So I'm feeling good about this. Let's go ahead and see if it works. The derivative of sine with respect to x is cos of x. And solving for dx by cross multiplying, we get du over cos x dx. Okay, let's go ahead and substitute this into our integral. The first thing we have is to change the bounds. It's a definite integral. We're doing a u substitution, change your bounds. So the upper bound is pi over 2. Sine of pi over 2 is 1. And then sine of 0 is 0. So make sure you're comfortable with your unit circle. Cos of x stays, there's nothing to do there. Times sine, and Inside the sign, we're replacing sine of x with u, so it becomes sine of u. And we're substituting dx with du over cos x. And notice that the cos x's cancel, leaving us with the integral from 0 to 1 of sine of u du. Okay, very simple. We know how to integrate that. We know the derivative of sine is cos, so the integral of sine, negative cos. So this is negative cos of u. And we're evaluating this from 0 to 1. Okay, so we're going to substitute the 1, and then we're going to substitute the 0. This is giving us negative, let's put that on the outside, cos of 1 minus cos of 0. So we get negative cos of 1, whatever that value is, you would leave it like this. Without a calculator, you can't solve that, just leave it as cos of 1. And this negative distributes to this one, turning it positive, because two negatives make a positive, and cos of 0 is 1. So the answer is just 1 minus cos of 1 unit squared. Okay, and we're done. Let's look at our next example. So in our next example, we have to evaluate the integral from 0 to 1 of 2e to the x plus 2 divided by e to the x plus x dx. So go ahead, pause the video, see if you're able to solve this on your own. So what I would do first is let u equal to e to the x plus x. Okay, this is a tough example, very tricky, but e to the x plus x, the denominator in this case, stands out to me because I'm thinking of the derivative. What's the derivative of e to the x plus x? Well, the derivative with respect to x is e to the x plus 1. Why do I think this is a good thing? Why is e to the x plus 1 a good thing? Well, here's where they're a bit sneaky in the question. What you have to do in the numerator is factor out a 2. Notice that if you factor out a 2, you're left with e to the x plus 1, which is exactly our derivative. So our derivative was there, but it was just hidden. So sometimes you might have to factor or manipulate it a bit in order to actually see the derivative. Very tricky, be careful for those. So we know that this e to the x plus x does in fact work. Let's go ahead and solve. Let me finish by solving for dx. We're going to do that by cross multiplying, giving us du divided by e to the x plus 1, which is equal to dx. So it's a definite integral. We're applying a u substitution. We switch our bounds. The lower bound is a 0. So if I substitute 0 into here, I get 0 plus e to the 0. E to the 0 is 1. So we're left with 1. And on the top, we have a 1. So it's 1 plus e to the 1. Whatever that number is, we'll just leave it as is. And on the top, let's factor out the 2 right away, leaving us with e to the x plus 1 on the numerator. And on the bottom, we're left with e to the x plus x, which we called u. So substitute this with u. And dx is being replaced with du over e to the x plus 1. So the e to the x's plus 1 cancel, leaving us with a 2 on top and a u on the bottom. The 2 is a constant, we pull it out. And we're left with the integral of 1 plus e, from 1 to 1 plus e, of 1 over u du. And this we've seen already, the integral of 1 over u, or 1 over x, is ln. So 2 ln of u, and we're integrating it from 1 to 1 plus e. So we're going to substitute our 1 and our 1 plus e. This is equal to 2 ln of 1 plus e minus ln of 1. Okay, ln of 1 is just 0, so the answer here is simply, we're subtracting 0, so we're just left with 2 ln of 1 plus e. Whatever that value is, you would leave it this way. Okay. And we're done. So let's take a look at our final example. So our final example here is a proof. We have to prove that for a, b, which are positive real numbers, then we have the integral of 0 to 1 of x to the exponent a times 1 minus x to the exponent b dx is equal to the integral from 0 to 1 of x to the b times 1 minus x to the a dx. So go ahead, pause the video, see if you're able to solve this on your own. So the trick to this problem is using the appropriate u substitution. Letting u equal 1 minus x, whatever's in this bracket is the trick. So we're going to start off with the left-hand side and move our way to the right-hand side. So letting u equal 1 minus x, the term in this bracket, works because the derivative du is equal to negative 1 dx. Cross multiplying, we get du, well, negative du equals dx. So we're dividing by negative 1 on both sides, that's why we have a negative here, and the dx comes here on top. So dx is equal to negative du. So this integral here, let's put a question mark here. This integral here is equal to, let me rewrite it. We have the integral from 0 to 1 of x to the a, 1 minus x to the b dx. That's our starting point, that's the left-hand side of the equation. We said this is equal to, we're using a u substitution, but it's a definite u substitution, so we have to change the bounds. The lower bound is 0. If you plug in 0, you get 1 minus 0, which is 1, so the lower bound turns into 1. And the upper bound is 1, so if we substitute 1 here, we have 1 minus 1, which is now 0. Okay, so we have now the integral from 1 to 0. This is an issue. X to the a is simply x to the a. And 1 minus x, we're replacing it with u. So we have u to the b. And dx is being replaced with negative du. Okay. So I'm going to take the negative and sit it in the front. So we have negative integral 1 to 0 of x to the a u to the b du. You have to remember, for a u substitution, we have to express this solely in terms of u. So the fact that we have an x here is not good. How do we rectify that? Well, we saw this trick already, where you go back to the original substitution. We have a relationship between x and u. So instead of writing it as x, we could move the x over. If u is equal to 1 minus x, if u is equal to 1 minus x, then if we add x on both sides, we have u plus x equals 1, and then subtract both sides by u, we have x equals 1 minus u. Isolating for x in this equation that we started with gives us a relationship between x and u. So we could rewrite x as negative integral from 1 to 0. X is being rewritten as 1 minus u to the a times u to the b du. Okay. So this is close to what we want, but the issue is we have a negative in front. How do we deal with the negative? Well, we know a property. We know that the property, if you have a negative, you could change the boundaries. Or by switching the boundaries, a negative pops out. So with that being said, using our property, this could be rewritten as 0 to 1. So we flip the bounds, a negative pops out, causing this to be negative as well. And we're left with 1 minus u to the a times u to the b du. And this completes the proof. Why are we done? Well, we're left with all these u's, but at the end, technically, whatever parameter you use doesn't matter. So the fact that we got it here written in terms of u, this is exactly the same thing as here, because we could switch the u's for b. I told you earlier not to use the substitution u equals x, but technically at this stage, if you use the u substitution u equals x, which again is useless in terms of solving the problem, but to make this, let's say to complete it, rewriting u and x, we're switching the parameters, we get 1 minus x over a times x b dx. And this is what we had. It's written in the wrong order, but you're multiplying, so it doesn't matter. When you're multiplying, it's commutative. 2 times 3 is the same as 3 times 2. So we get back what we started with. Okay, so this is the proof. I hope this video helps, and I hope you have a better understanding of u substitution. The only difference here for definite integrals, remember, you have to switch the bounds of integration, okay? So don't forget. So keep practicing. I hope this helped, and I'll see you in the next one.